Uh, Good afternoon. I am Sandeep Maithani and I basically work in the Urban and Regional Studies Department at IRS. Today, we are going to discuss something about remote sensing applications for urban and regional studies. In this, we will discuss how remote sensing and GIS technology has been used for to deal with the various aspects of urban and regional planning. So, first of all, we'll discuss what is the importance of urban studies. So, you see, urban areas, they are basically engines of growth and they provide service and economies of scale, and they also contribute significantly in any country's economy and employment and development. So, urban areas are basically a pull factor that drive the economy of any country. But over the years, we have some issues have been identified because of the rapid and unplanned growth of the urban areas. Mainly, the first one is the lack of open space, lack of adequate infrastructure facilities like water supply, sanitation, sewerage. These are some basic infrastructure facilities which are still lacking in our country. Okay. Thirdly, the overcrowding and the congestion, which leads to a high population density, and such high dense growth in lack of adequate infrastructure leads to a very low quality of life. The mushrooming of slums, which are basically unauthorized, unplanned settlements where we have a very low level of infrastructure facilities and the living standard is very poor. Last is the lack of drinking water and sanitation, as discussed previously. That is the basic infrastructure facilities. And nowadays, the Amrut 2.0 scheme has also been launched by Government of India to ensure that proper drinking water and sewerage facility is provided to each home in the urban area. And lastly is the solid waste disposal, because currently a lot of solid waste is being generated in our urban settlements, human settlements, and sustainable and safe disposal of this solid waste disposal is also one of the issues that has come up in the urban areas. Especially, we are having a lot of environmental problem and emission of greenhouse gases from the solid waste disposal sites. And all these have basically contributed to a poor environmental quality or a poor quality of living. And so there is so in order to address these issues, there is a need for timely and updated or current and accurate geospatial information which can help in better planning of the available resources and ensure a sustainable urban development in our country and in most of the urban areas in the developing world. Now, before now coming to the main topic of this lecture, what are the data requirements for various urban studies? So you see, for physical infrastructure, like mapping of physical infrastructure, the land use, land cover, the road infrastructure. Secondly, we have to define the requirements for a legal framework, that is how remote sensing and GIS can help in development of master plans, especially as we are now doing in the Amrut 2.0 scheme also. Social understanding, that means the stakeholders' characteristics and their aspirations, and the connection between the city and the society. And lastly, it is the fiscal management, especially the taxation. How using remote sensing we can ensure a better tax collection by the municipalities. So, in order to address these physical parameters, the legal framework, the social understanding, and the physical management, we require remote sensing data sets. The remote sensing data sets can help in basically all of these four aspects of urban planning. Till now, you see, we were getting this remote sensing images. And now we are also using drone imageries also, which are also high resolution imageries. And from those, we can interpret a lot of things, the commercial areas, the residential areas. And previously or nowadays also, we have image interpretation, which is manual. That means we recognize the objects using elements of image interpretation. But with the development in the technology and the computing power, now most of this process has been automated. And for those which are using we are using various machine learning dependent algorithms uh, to classify the objects, or for information retrieval from the high resolution satellite or the drone imageries. We are now going towards machine learning algorithms. Like a number of case studies have been reported where they have extracted the building footprints, infrastructure, road networks, etc., with minimum human intervention from remote sensing imageries. Now, you see, coming to the geospatial technology for urban studies, the data sets we are using is remote sensing. Secondly, we are using the photogrammetric techniques, yeah, especially the digital photogrammetry and close range photogrammetry. These are basically used for generation of digital elevation models or digital service models, so that we can have a better understanding of the building heights and the topography also in the urban areas, which provides a lot of input in the planning of infrastructure facilities, especially the estimation of the cut and the fill operations. As I told you, slowly and slowly we are now shifting towards use of urban this unmanned drones or UAV. And Amrut 2.0 scheme basically emphasizes the use of this UAV only, because in Amrut 2 we are covering the towns between which are having a population between 50,000 to 1 lakh, 50,000 to 1 lakh. That is the class 2 towns. And these towns are the spatial spread of these towns is not very large. So for mapping of these small towns, now we are using UAV or drones imageries compared to the satellite imagery. Then for this location based services and for mobile mapping, we are also using the global navigation satellite systems. Especially this location based services is being used by a number of people. And we are also using some field sensors like the ground penetration radar for mapping of this water pipelines and sewerage pipelines. And automatic weather stations are also being used for monitoring of the urban microclimate. So you see, apart from that, we are also using sometimes the traditional survey instruments like the theodolite and total station also. So you see, we are using in urban planning, we are not only using satellite imageries, we are using satellite imageries, we are using data sets from drones, then we are using GNSS data sets, and using these data sets, we are using photographic techniques for evaluation of, for basically to extract the DSM or the DEM from this imageries, which can be used for cut and fill operations. And this sometimes we are also augmenting this remote sensing data from field-based sensors, namely like the GPR, which is used for mapping of underground infrastructure facilities, the automatic weather stations also we are using. So, and the traditional total station, of course, satellite are now also you can use, but normally we are using the total stations. So, see, we are using a data from a number of sources for various geospatial technology for urban studies. So you see, why we should use remote sensing data for urban and regional planning. The first thing is we can identify the behavior of a land over a specific time. So we can monitor especially the land cover changes, the temporal land cover changes that have taken place. Uh, and this provides us with the wealth of information. And secondly, this data is digital, so we can easily process it using various softwares or machine learning algorithms. And then transmitting of this data is very easy. Okay. And we can also use spatial query and mapping function of GIS to analyze the existing situations. Like we can use a GIS, a special query in a GIS software to find out like how many hospitals they are located within a circular buffer of we can say 100, maybe 1 kilometer. So these kind of special queries are very good if you want to find the nearest hospital, or maybe you are interested in finding the nearest petrol pump as you are getting in the mobile apps. So all these things can be done using remote sensing, and then developing this spatial database in a GIS software. So the first thing for urban mapping is the spatial resolution. See, the spatial resolution means the smallest object that can be resolved by the sensor. So the higher spatial resolution is desirable in urban areas as we have densely built and feature comparatively smaller in size. So for urban studies, normally we go for a high resolution imagery and a minimum of 4 pixels within an object to identify. To identify an object, we should be able to basically identify 4 pixels. Apart from that, the role of shape, size, texture, orientation, and pattern, shadow, this is very important. And for making a high scale land cover map or land use map, the spatial resolution is a very important thing. Second is the spectral resolution. That is the number of spectral bands which the sensor is sensitive to. So in this we are using panchromatic band, which basically has a one large band, to which then we have the multispectral band, which images the same thing in multiple bands, and then we have the hyperspectral band where the same object is imaged in number of bands, or you can say thousands of bands. Then the advantage is if we are using multispectral or hyperspectral imagery, then we are basically better able to identify the features or differentiate the features, right? Third is the temporal resolution, that is the time needed to revisit or acquire the same data, the time taken to acquire the same data. Okay, so especially for very dynamic phenomena like urban sprawl or crowd management, especially we require data which has got a very high temporal resolution or a very high revisit facility. And last is the radiometric resolution, that is the number of bits or the range of numbers that are generated by the sensors. So if you see the radiometric resolution is high, it is 12 bit or 16 bit, then we can identify more shades of gray and we can better identify the distinguish the features. But if the resolution is low, then we cannot detect the small differences. So whenever we are going for urban mapping, so first of all we have to decide what is the spatial resolution, what is the spectral resolution, what is the temporal resolution, and what is the radiometric resolution. So normally we go for a higher spatial resolution. Of course, spectral resolution, if it is high, then it is easier to identify the objects. The temporal resolution should be high, especially if you are using, you are monitoring something very dynamic like a crowd or a traffic flow. But if you are monitoring the urban land cover transformation, then you don't require a very high temporal resolution. Maybe a 1 year imagery may also be good. And lastly, the radiometric resolution. They told you higher the radiometric resolution, better, more shades of gray you can see, and so better the objects can be differentiated. So you see here we are showing some imageries. So this is basically a 20-meter spatial resolution and 200 bands. Okay, this is basically a hyperspectral data. This is a multispectral data which has got 4 bands, 4 optical bands, but the spatial resolution is 2.4. And this is a panchromatic imagery which has got 1 band and the resolution is 0.6 meters. Okay, so you see the difference is here you can see more details, you can identify or distinguish more features, but here we have the color also, because we have taken imaging the same object in different bands. So sometimes based on the spectral resolution or the difference in the spectral curve, you can distinguish more feature. Of course, here the spectral resolution has gone down, but the spectral resolution is very high, while the spatial resolution is comparatively low. It has gone down from zero point 0.6 to 20. So here you see you can identify more features based on the spectral signature. So each image has got its advantage, each sensor has got its advantage and disadvantage. Here we are having a low spectral resolution but higher, we are having a low spatial resolution but a higher spectral resolution. Here we are having a high spatial resolution but a low spectral resolution. And this is somewhere in the middle where we have got a optimum spatial resolution and optimum spectral resolution also. So you see, regarding the radiometric characteristics, you see, this is a 2-bit data. So you see the radiometry is very poor. You cannot distinguish many features. Then this is a 4-bit data. So you can identify more objects because, and this is a 6-bit data and this is a 8-bit data. So you see, as the number of bits are increasing or the radiometric resolution is increasing, you can identify more shades of gray. So you can identify more objects in this, okay, compared to the 2-bit data. But only thing is, if you make it, you can say, why don't we increase it to 16-bit? Yes, we can increase it to 16-bit. We can differentiate more shades of gray or more features. But only thing is the data set volume also increases. So that also has to be taken into consideration, like what is the volume of the data, because accordingly our hardware and software configuration have to be updated. So you see, this is the temporal characteristics. You see, this imagery are taken at in the 4th month in the in 2003. This is taken around 2010 and this is taken around 2020. So you see, in this is called as temporal resolution. You can identify this area was not having much growth, but slowly in 2010 some growth has taken place, and if you see in 2021 the built up area has increased at a very phenomenal scale. You see a large, this is same, but you see a large settlements have come up. So you see, when we do urban studies, so we have to decide what is the spatial resolution, what is the spectral resolution, what is the radiometric resolution, and what is the temporal resolution. So depending on your objectives, you decide. There is nothing like a best and nothing like a bad. Everything is okay. Depending on your objective, you have to basically decide which you will use data, what spatial, spectral, radiometric, or temporal resolution. As I told you, if you are studying phenomena like urban growth or built up growth, then you require data of at least 10 or 5 years. But if you are studying like traffic flow or crowd management, how crowds are basically, how the people are gathering at a place, especially if you have a very public functions, then for that you require data of high temporal resolutions. Okay, so from the relationship of planning system, we can see normally in this we have first got a perspective plan. So perspective plan is more of a philosophy. It is much less of spatial data. It is much of how the system or how the local authorities they want in future development process should happen. Then we have the regional plan at a lower level, then the local plan or master plan, and then the annual plan. So you see, as you come down, you have more and more details. The map scale becomes large. Here you may be talking about 1:4,000. Here you will be talking about 1:20,000 also. And here it is more of the concepts and less of drawings basically. So as you go down the hierarchy, you see, you can find out like the level of detail increases. Okay, so the resolution of data also you can choose accordingly. If you are making a regional plan, you can take a coarse resolution image of maybe 30 meter or 20 meters. But as you go down, you make a local plan, annual plan, then here it is more spatial in nature and you require high resolution data sets, or maybe a high resolution, a drone imagery, which is basically a high resolution data set. So these are some of the normally used mapping scales for different planning levels. You see, when you are making this regional perspective plan, you can go for a moderate resolution or low resolution, that is more than 30 meters. and the mapping scale is 1 is to 50,000 to 1 is to 1 million. When you go out to a district development, you are using a medium resolution data sets, that is 4 to 30 meters, and the mapping scale is from 10 to 50,000. And when you come down to a micro level or village level, then your resolution is 0.6 to 4, and then your mapping scale now comes to be on 1 is to 5,000. Why we are saying 4,000, 5,000 is because most of the cadastral database has been made at a scale of 1 is to 4,000 or 5,000. Okay, so some kind of study you can do is if you're using a sprawl analysis, transport network, or you are using level 1 basically. Level 2 is urban suitability analysis, mapping of major transport, upgradation of city maps, and last is slum topology, mapping of property, this parcels or footprint map. Then for this population estimation, tax assessment, we basically use one maps of from 1 is to 5,000 to 1 is to 1,000. So you see, as we discussed earlier also, depending on your planning objectives, that or your planning goals, or your what you want to do in the urban area, basically the scale of the map is decided, and then based on the scale of the map, we basically try to find a data set which fulfills most of the our requirements. Basically, a data, sometimes you will not find a data set which satisfied all your data or your requirements. Then you have to find out which is the most optimum for you. Okay, so first you decide the objective, then you decide the mapping scale, and then you try to find out which is the data set which fulfills your requirements. Okay, so what we have got is basically urban planning. We have got, as discussing, is various scales of map. Like if you are doing a level 1, that means you are doing basically a land cover mapping, and a regional level, so scale of the map is around 1 is to 50,000. And the land cover is also very broad, like built up, non built up. When you come to a development plan, your scale comes down to a 12,500 or sometimes 20,000 also. And then you talk about rural areas, residential areas, in urban areas, commercial, industrial. Then when you come to a zonal plan, you fill in more detail. Like residential, it's a high rise, medium rise, low rise, slum. What is the industry, heavy, or it is a basically the industry can be heavy, light, or others, commercial, recreation, and the scale also increases to 4,000. And 1,000 it becomes too detailed, like high rises, apartment, or flat, and all those things. So you see, one thing which you have to understand is as the uh, planning level goes down from 1, 2, 3, 4, the scale of the map also becomes large. And normally, the data sets you require are of more high resolution as you come down to level 4. So, the emphasis is you first of all choose what scale of mapping you have to do. Then you choose the scale of, you see what kind of, you have to make a perspective plan, development plan, that is the first objective. That defines your scale of mapping, and then that scale of mapping decides the data products you have to use. Whether you have to use the low resolution, medium resolution, or a high resolution, or maybe a very high resolution also. It depends on the scale of the mapping, or the what is your aim. You are making a zonal plan, or you are making a project scheme, or you are making a perspective plan. This all depends on, decides the scale of the mapping, and then that decides the data to be used. And you see, the things we can make out from remote sensing is, this is a remote sensing imagery, so you can make out which, this is a planned area, high dense planned area. This is a low density planned area, because you see the houses are quite separate from each other. Here you see the buildings density is very high, they are quite near to each other, but still we have got a regular road network, the plot layout, the building layout is regular. But you see here is, here the layout is totally irregular. So this is a high density planned, and this is a high density unplanned. How we can say from remote sensing imageries, you see here the buildings are having a regular layout, the roads are well laid out. Here you see we don't have a regular layout of the buildings, neither we have got a regular layout of the roads. So these are two things which help you to distinguish broadly whether it is a planned or an unplanned settlement. Similarly, you see these are low density, but you see the houses are regularly laid out, well planned area is there. This you see is basically a low density, but it is rather unplanned because we don't have a regular layout. So if you look at high resolution imageries of urban areas with a bit focused, you can see how the first thing you should try to do is what is the density of the buildings, okay, and secondly is what is the layout of the road network, what is the layout of the buildings on the ground, because that will help you in finding out whether it is a planned or it is a unplanned high density, medium density or low density. So these features we can find out from a high resolution satellite imagery. Now you see some things here you can say, you can broadly find out this appears to be a residential area with well laid out buildings, and this is a low density, but there are some features which you can easily find out from the remote sensing urban features. This appears to be a commercial area, you can see, okay. You can see here the building size is very big. We have got tin shades also. So this appears to be a industrial area. Here you can see this is basically railway lines. You can see linear features. So this is basically a transportation. Okay. Here you can see this. See, this is a complex which has got a very regular layout. We have got a lot of open areas. So it appears to be a institution. Here you can see it is like this, so it may be a auditorium or it may be a park. Okay, so these some features you can easily find out from the satellite imagery because of the peculiar size, peculiar shape or the peculiar pattern. Some features you can find out like stadium, large institutions, maybe large parks, urban parks or green areas, but for some you have to go to the ground and do a survey and then you make a land use map. So now the geospatial applications in urban planning are basically we can use remote sensing geospatial technology in inclusive planning, that is for vulnerability analysis and mapping of informal settlements, in urban governments, that is municipal taxation or property taxation, municipal GIS, demographic studies, urban cadastral studies, and monitoring of urban encroachments. Third is urban environment, urban landscape, urban green, solid waste disposal, site selection, urban heat island, UHI, urban pollution, microclimate, solar potential. We can use them for urban environment studies. We can use them for regional planning, that is regional plans and boundaries, sustainable development, socioeconomic disparity, etc. Then in heritage conservation also, namely the application of close range photogrammetry and terrestrial laser scanner in analysis of various heritage buildings also. Then we can use them in urban design, that is a 3D visualization using LiDAR, regeneration, redevelopment analysis, and rainwater harvesting. We can use them for urban utility, that is a surface, subsurface utility mapping, transportation and mapping. And then for urban hazard, yes, remote sensing has got a land of use because it can use for hazard mapping and analysis like seismic hazards, landslide hazard or flood hazards, urban floods, microseismic studies. So these are number of this circle shows you basically what are the basically various domains in urban regional planning where geospatial technology or remote sensing in GIS can be used. So first of all, this is basically we have done for Hyderabad and Pune city. Now we are trying, I will show you some of the applications like we have used this remote sensing to do temporal images to do a urban growth monitoring of 2 cities, but similarly you can do for a number of studies like and for this there is one site which offers the GSL, that is called as Global Human Settlement Layer. This layer is you can see the address. You can go to this site and you can freely download the built up area, the built up density, the population data also for basically 4 epoch, that is from 1975 onwards at a resolution of 30 meters. And these areas of higher development density in this data set are very accurate and reliable. Although rural areas show low accuracy because of misalignment, okay, but for urban areas we can this data sets is very good, and you can see you can get a data set of 4 epochs, that's 1975, 90, 2000 and 2014 at a resolution of around 38 meters, and this data is totally free. So you can visit this data, that is by name of GSL, Global Human Settlement Layer. Okay, so we have made this using this global human settlement layer only. Okay, then second is we have used this remote sensing imagery, high resolution imagery for mapping of the urban footprint or urban mapping of the building footprint, we can say. So we are mapping the building footprint, the road network using this high resolution imagery, and then this can basically be used in for taxation or for monitoring the illegal encroachments. This kind of activities can be mapped. So we are using this, and you can see these roads, we can map them and we can get them. Then, as we told earlier, we have used this remote sensing imageries for monitoring of urban sprawl, like of Dehradun city from 1987. We have taken the imageries, and then we have made a windrows type of a diagram which shows where the growth has taken place, which direction the growth has taken place, where less growth has taken place, and where more growth has taken place. You can see most of the growth is in this direction and in this direction. Then secondly, you analyze why this growth has taken place in this direction only. And of course, you can make a bar chart also out of it, identifying the pattern of the growth. These again are ANN based model we have run, where we have simulated the growth of the city in response to various measures using artificial neural network. So this shows if the growth takes place as usual, where the growth will take place. Okay, this is basically a compact growth scenario. So here, if we don't want the city to grow in like this, we want the city to grow in a compact manner, so that high dense manner, so that we can have where the future growth will take place. And this, instead of having a compact growth, if we want to have a hierarchy of growth, or we want to promote multi hierarchy centers, how it should be there. So you see here, using inputs from remote sensing and GIS, we have basically simulated the growth of the urban area in response to various policy measures. Then this is another application where we use the high resolution data, ICONOS data, for mapping of slum areas which are illegally built and where the poor living condition is very bad, or the level of sanitation and the quality of life is very poor, or because the infrastructure facilities in this area are lacking. And you can see you can say how we identified these things, slums basically. So as we discussed in the previous slide, based on the layout, the road network structure, size of the housing units, which we can see from the remote sensing imagery, we could gauge where are the slums. Then using the high resolution data, we have made a footprints of the various buildings in the slums, and then we have also by ground survey tried to find out what is the level of sanitary, what is the roof, what is the wall, type of wall, mud or kacha pakka, all those things we have done for the slum areas. And you see, nowadays you see the buildings, they are not only growing in a 2D, now they are also growing vertically. So there is an urgent need basically to map the Z direction also, how much growth is taking place in the Z direction. So we call as the space use mapping, okay, for multi-story buildings. So using aerial photographs, high resolution, stereo pair and lidar, we have tried to map the number of stories and what is the kind of activity going on in each story. So this kind of data sets will be useful for the municipal authorities. So they get an idea like what is the level of infrastructure that is required here and how much taxation also we can collect from this area. So this is called as a space use survey, where we are not talking about the XY only, but we are also talking about the third dimension, that is the vertical dimension. Of course, as you told earlier, using these imageries, we have tried to basically make a footprint map, and then those footprint maps have been used for urban taxation. like using the unit area method, we have tried to estimate like how much tax should be collected from different municipal wards, and is that tax coming or not coming. If it is not coming, then we can do a resurvey also. Okay, then we are also using the location based service, as I told you, like the service area of a city park, how much schools, the schools they are serving, how much population, like we have made a 1.5 kilometer buffer. Then how much time it takes for a fire extinguisher to travel to a particular place. So how much area is covered in a 10-meter time period, that we have to take mind. And then also we have used this location based services for making a tourist information system. So if a tourist come, he knows how much distance it will take him by bus or auto to reach various destinations from the railway stations or from the hotel. So this is we are also using this location based services also. We are developing using inputs from remote sensing and GNSS also. Then we have also used this remote sensing imagery to find out the rooftop solar potential assessment. Like if our built up area is this much, how much is the, what is the sunlight and what is the insolation basically. Okay, so how much is the rooftop solar potential for various areas, we have tried find out, so as to ensure a sustainable development. So this DSM which we have made, this we have made using a, you can make using a high resolution remote sensing products also, or from ground survey you can make a DSM also. Then using the GP and all those things, we have tried to study the water utility distribution modeling in our study area. You see, this is the data from a GPR which shows you like what is the depth and basically what is the type of material of the pipeline that is there. Okay, and then using this inputs, the building typology from remote sensing, pipeline distribution map from a GPR, and then a location of walls and household distribution, we have tried to estimate what is the pressure or head loss in different areas. So it allows us to have a better planning of the infrastructure facilities, or we can analyze the real situation of water distribution, supply and demand for different water supply areas of different wards of a municipal area, right? And of course we know like in nowadays, because of increased human activities like industrial traffic or increased use of this commercial areas, lights that are being used in the commercial area, because of pollution, the urban areas, they have got a higher temperature compared to the surrounding area, contiguous areas, you see. So you see here it is high, here it is low. So this is called as urban heat islands. So it is something like that. In the city there is a higher temperature compared to the surrounding suburban area. So using satellite imagery also, we have tried to map how the urban heat island is there, how much area is affected, and what is the temporal variation in this urban heat island, okay, in a daytime, in a day, in the especially the night and the day. Then you see in the previous time the heat waves also increase, which leads to a very uncomfortable situations for the population. And here we have also tried to map the distribution of heat waves temporally over the last few years using remote sensing and data sets. And lastly, the urban hazards, as we discussed. So here we have also tried to identify like how much area has a day, what is the rainfall intensity this much, how much area will be inundated and flooded, what will be the depth of the flood water, and based on that we have basically tried to make a urban flood vulnerable areas basically using some inputs from remote sensing imagery like the cartosat and LIS4 and airborne radar, and these have been all combined in a storm water management models, and then we have tried to map out, try to find out which areas that are at risk basically. Okay, this is again one study we have done where we have tried for a ward, where we have tried to find out like in case of earthquake which areas are more, which buildings are most vulnerable, what is how much population it at risk, and then we also try to find out like how which road has a higher probability of blockage, which has got less probability. For this we have used very high resolution satellite imagery for mapping of this footprints, and plus some ground data we have done. So you see, in all those in studies, remote sensing is basically a spatial data provider, while lidar and all other things, they help provide the other data also, augmented by some ground data. In a GIS environment, we can conduct a number of case studies for covering various aspects of urban areas, as we discussed earlier, right from urban flooding, urban seismic, urban pollution, urban, this you can say, rooftop potential, solar rooftop potential, and urban green spaces mapping. They are just to name a few, but we have got n number of potentials which we can do. Okay, we can make a development plan. So in all those things, we use a amalgam of this remote sensing data, ground data, data from GPR or some socioeconomic data, and finally then we try to develop a application of these data sets in the urban domain. So in the future, you see the geospatial needs are basically, we require a very high resolution data set in that is more than around 0.5 meter or more, especially in the visible near infrared and the short wave infrared. Then we require high resolution data with more than 8 bands. Okay, then we require lidar data also, so that will give us more of height information. And or areas which are having a cloud cover, we require a high resolution satellite, this synthetic aperture radar data, basically at resolution of 1 meter or more. Of course, hyperspectral data with high resolution is required, so that we can better identify the uh, various things or the various features, urban features present on the ground, basically. Okay? Then high resolution thermal data is also required if you want to do studies like variation of urban temperature during the night and the daytime. If you, especially if you want to monitor the urban thermal domain, then we require high resolution thermal data sets, maybe 5 meter or more. So that will basically be very useful for urban heat island, all those kind of study. And to for location based services, we require high accuracy navigation systems or GNS systems. And if you want to study things like urban climate or urban microclimate, which is also one of the emerging areas now lately, then you require basically thermal data set at a resolution of around 100 meters. And but the only thing is, if the resolution is low, the temperature, spatial resolution is 100 meter, but the temporal resolution should be an hourly. That will help a lot in monitoring the day and night variation in the temperature. If you want precipitation data sets, it should be maybe 1 kilometer, but the temporal resolutions will be high. Same for total ozone. You see, if you want to do some climatic studies, then of course your resolution will be maybe low, but your temporal resolution should be high, because you want to monitor the various parameters of urban climate. Okay, so thank you very much for your attention. This is more or less in a nutshell how remote sensing and can be used in urban and regional planning. Thank you. So if you have any questions, you can please post them. So there is one question like, when we are treating the entire slum as a homogeneous area, so is there a new model for distinguishing slum according to personal river? Yes. You see, if you are using remote sensing data sets, then from that you can easily find out the size of the slums and the layout of the slums. So based on these data sets, you don't need to treat the entire slum as a homogeneous area. You can find the heterogeneity based on the building type, building size, layout of the buildings also. And yes, if we are feeding this data in a GIS, then using the proximity function or the topologically basic, it's a proximity function, you can find out which slum is near to the urban areas and which is further. Sorry, which is near to the river and which is further away. So you can, using the this GIS operations of proximity, you can easily find out slums in proximity of rivers or any other feature and those that are far away. Okay. So one question is, what are the tools used for pre-processing of hyperspectral, multispectral, and satellite data? You see, when you buy these data sets from a vendor, uh, certain degree of radiometric and geometry corrections are already done. Otherwise, there are a number of commercial softwares you can use for pre-processing, or you can write your own programs and you can do it. So it depends on how much comfortable you are. If you're too much comfortable with coding, you can write your own program for pre-processing it, or you can use any freely available image processing software, or there are some commercial softwares also. You can use them and pre-process the data. You see, if you want to do vehicle movement, the only thing is this kind of data is very dynamic. So you require a satellite imagery with a very high temporal resolution. So I would advise you instead of satellite data, you can use a drone imageries, which have got a higher temporal resolutions for mapping the vehicular movements. Or you can use a GPS receiver put on the top of the vehicle, and then you can easily find out where the vehicle is moving for supply chain management. So it's more of a GPS based application than a satellite based application. Okay. Then one question is there any? Yes. The question is, at city scale, can I use Landsat 8 thermal data? Yes, you can use. Yes. And you see, if you're using it for thermal mapping, so no need to much atmospheric correction is there, because most of the algorithms, they take into factor the atmospheric fraction. So you can use that data, apply any single window or mono window and algorithm and go with it. Yes. See, atmospheric list data sets is there, so you can use any commercial software, or you can use a free software again for doing atmospheric corrections. But normally, the vendors also, they do a certain degree of atmospheric corrections. So these are all the queries we have presently. And if you have more queries, then you can write at our this address, and we will address. We'll send you. You can send a mail, and we will send you answer your queries. So that's all. Thank you. Thank you very much.